a code storage website.
Okay.
Like if you look here, it's all code.
Just like store on Google Drive or something.
Yeah. So like here's like a do file, right? Just keeps code. It's pretty cool. All right, we are starting. Click, please. Yes, let's go. Full screen. I'm gonna assume that there's not gonna be anybody in the chat today, so that's how we're gonna roll it. Hello and welcome to the final review. I have gone through just the thoughts and feelings and intents of my heart, and I've come up with a list of topics that I'd like to get through with you guys. No particular reason for any of these topics, just just some deep sentiment and feeling in my heart, right? So let me just give you. No, definitely not. I didn't write the test. Like, I didn't write any questions on there. I've never seen it before, so just keep that in mind. Take this with a grain of salt, if you will. We're going to talk about bias and efficiency and how they met. From what I understand, yesterday you had kind of a longer review of correcting bias than maybe you were meant to, so we probably won't touch on that one super much. But we're going to talk about how being more confident means you have wider intervals. Nice haircut, Khalil.
It's a summer cut.
Yeah, that's what I'm talking about.
There we go.
I hope you think you did it.
Rejecting the Null Hypothesis, law of large numbers versus the central limit theorem, passing E's and B's through, formulas for mean and variance, how to read a state of help file, how to read the gen command, getting the mean and variance from data across different days, formulas for correlation and covariance, finding confidence intervals, hypothesis testing, formulas for beta hat 1 and beta naught, which she calls B and A for reasons I still don't understand. Adjusting your estimators for bias, we will probably not touch on that one, but we'll go over some event trees, some conditional probabilities, going from the PDF to the CDF, making PDFs valid, marginal Pdfs, conditionals with PDFs, percentiles, so on and so forth. So lots to cover today. We're going to try to breeze through some stuff, and unfortunately, I haven't had quite as much time to organize it as I would have liked. So let's see if we can knock a couple of these boys out. But before we go, any of these that you guys are feeling weakest on that you'd like to cover first? Just, take a second to look. Brenna's got a hand up. Bias is still funky. We can talk about bias too. Absolutely, that's fine. What's cooking? I'll put a little star there. Bias. Ka-chow. And are you talking about adjusting for bias or just finding bias and the concept in general? Cool. Okay. Yep, Tyler.
For sure, just look at the review of regression and then
Regression, PDF, CDFs. Yeah, it has been a minute. All right, and we'll do marginals as well. It's gonna be a little funky because I gotta look way down because normally this is up here. It's kind of funky, but.
Question.
Yes, sir.
Are we gonna do stuff from first?
I mean, there's a couple the event trees or conditional probability formulas. Those are on here. Yeah. So, yes. You missed my explanation of how I came up with this list, Khalil, but I just pondered on the thoughts and intents of my heart, and it's definitely not every topic you'll see on the test. It would never ever be that. That would be. No. It was just stuff I was feeling, just stuff I was thinking about, Nothing really related to the test. Not it's a review, but it's just a vibe review, kind of, Anyway, is it weird to see me there and here? Yeah. Well, what can you do? That's just, what can you do? Oh, you know what I can do, actually? I'll do it later, actually. Here. We could just go like this. There's the chat right there, but oh, there's two watch. Oh shoot. Okay, never mind. I guess we're gonna have to go like this then. Can't wait to review. There's Sam. That's what I'm talking about. Well, I guess I gotta keep the chat up then, huh? Let's go like that. Can I see the chat? No. Well, bad news. This is what you're stuck with. What can you do? Okay, first thing let's talk about is which one do we want to do first? Let's just talk about PDFs. Let's do that one first, because we're going to build off of stuff like that, right, when we start talking about bias. So, probability, distribution, or density functions. One thing that you guys didn't realize at the beginning of the class is that every time that we'd said, like, X has a PDF, and that PDF is like, you know, let's call it x squared plus 2 if X is within the interval from like 0 to 1, and then 0 otherwise, right? So one thing you may not have realized when we were writing stuff like this, is that big enough for you guys to see, generally speaking? Okay. One thing you may not have realized when we were doing this is that writing this PDF like this out is actually an explicit way of saying X is distributed with some funky distribution with like parameter like X star plus 2 or whatever, stuff like that, right? And not really with like a parameter, because that would be more of like an expected value, but like this is an explicit way of saying X is distributed in some type of way, right? Got me feeling some type of way. So what that means is that there is like an expected value of X. It's random here, but it does have like a certain probability distribution. In fact, if we were to graph it, this one right here, if I graphed this probability distribution function, it would kind of look like this. Well, from 0 to 1, right? So here's 1, here's 0, here's X, here's f of X, right? The probability density function. It would start at 2, and it would kind of go up, right? And then it would stop. And so this would be 100% of the probability of X right here is underneath this graph. Now, you didn't probably realize this while we were talking about PDFs in the past because we didn't graph them so often. Pardon. But the whole reason that moving from PDF to a CDF like can give you probabilities is because you're integrating PDFs, right? If I want to find the probability that X is less than 1/2, right, then I want to find this area right here. Does that make sense? Okay. These probability distribution functions represent, not technically, but you can think about it as representing the probability of finding any given, like, one value of X. Like, what is the probability of 1/2? Well, we don't know the exact probability of 1/2 because that area has no width, so it has no area. But if you go just to the right and just to the left of 1/2 and create a tiny little rectangle, find the area of that, that's the probability of getting 1/2, right? So let's talk about that. There are two ways I could find that blue highlighted probability right there. From this PDF, probability distribution function, I could calculate f of X and then plug in 1/2. I could do that. CDFs are just integrals of PDFs. So I could integrate the entire function from like 0 to X squiggle, or however we're going to do it, and then just plug in 1/2. I can do that. Or alternatively, I can just integrate from 0 to 1/2 the PDF, right? Because I only want to go from 0 to 1/2. I only want that much area. The trouble with doing this at all right now is that I can already tell you this PDF is not going to be a valid PDF. Why do you think I might say that? The area underneath the curve definitely is going to be more than 1 here. Like, it's at least 2, right? Just from this rectangle. And that's a huge problem. Why is that a huge problem? Somebody tell me why. Yeah, you can't have a probability that's over 100%, which, you know, clearly. So there's two things we could do. We could come up to here, right? Let's give ourselves a little space. we could put some scaling constant in k. And it would probably be less than 1 in this case, right? We can take the whole distribution and just scale it down so that the whole area under the curve is only equal to 1. Pardon, sorry. Allergy season got me tripping, brothers. Alternatively, all right, instead of putting this k on here, we could just leave this function how it is, and we can modify the domain of x. I don't remember if we ever did this on the homework, but we could like put a k in here and find what the k would have to be. How would I do that, potentially? Let's think about this. Well, if I have the bound of x from 0 to k, let's stop calling that 1/2, and let's call this k now. Don't know what that's going to be. Any ideas about how we might go about doing this? I could integrate from 0 to x and set it equal to 1, or I could integrate from 0 to k, right? If I integrate from 0 to k, figure out that whole equation, subtract the 0 version, and then I just solve for k after setting it equal to 1, that would work, right? It'd be functionally the same thing. In fact, I'm going to show you how to do that, right? So let's integrate from 0 to k. And again, k here can be anything. We don't know what it is. We just know it's going to help us probably bring x in so that we're only looking at 100% of the possible outcomes of x. So 0 to k, x squared plus 2 dx. This is going to turn into 1/3 x cubed plus 2x evaluated from k to 0. Now the nice thing is when I plug 0 into this, both of those terms are going to disappear. So all I have to do now is I set 1/3 k cubed plus 2k equal to 1. Right? Because I need this to integrate to 1. Is it negative? Is what negative? No, because I'm evaluating at k as my upper bound, and so I do the upper bound minus the lower bound. If I wanted to adjust it to the left, or adjust my leftward bound, I would make it negative. Absolutely. But then it wouldn't be 0. It'd probably, I want it to integrate, like, I want the bound to be k to 1, potentially, or like k to 2. I'm not going to work through the rest of this with you. I think all of you have the algebra skills to be able to solve for k here. And if you were to get a problem that looks like this on the test, it probably won't have an exponent in it, but I don't know exactly how my heart feels about that one. So just keep that in mind. This is what that would look like, right? This is the same functionally as putting a k like constant in here and then just integrating the k and then solving for the k. You just have it in a different spot, right? Jed.
Why is this the same functionally? Because it feels like we're restricting it to, like the slopes are different. Like we're restricting it to slower slope. But if we scale it down, then we have the same kind of like increase on the graph.
I mean, so when I say it's the same functionally, I don't mean it's like gonna completely leave everything unchanged, right? Like if I put a k, if I put a green, let's do green just to clarify this, right? The blue k, what it's doing is it's taking this line and it's moving it this way to something like that, right? That's what the blue k would do, and that's what we've done right here. Alternatively, doing a green k would basically take it like this, make it a little flatter over the same. But the functional idea is you need to shrink the area under the curve to be equal to 1. Whether you do that by adjusting like the actual range of x, or whether you do that by shrinking the actual PDF, same like idea, right?
And so integrating using both of these methods should give us the same result, right?
No, they won't give you the same result.
So how do we know which one to use?
It will tell you which one to use because either we will put a k in the equation or we will put a k in the bounds.
Gotcha.
And then you just get to figure it out, right? I don't think we've ever given you a k in the bounds before, but we have given you a k in the function, and I just wanted to point out that like the fundamental what do I do to solve for this k is the same in both cases. Integrate over the bounds, set it equal to 1, solve for k. That's pretty much everything we'd need here. I will also point out while we're here, let's assume that this k is here, and let's call it a valid PDF now. Assume that we've solved for the k. Pardon. Just to get to the CDF in general, we're going to want to integrate from 0 to x, our little x squiggly function, dx. And we don't have to set this equal to anything, because we're not actually trying to adjust the PDF anymore. We just want to know the CDF, maybe so I could plug in like a 1/2, or maybe so that I can just set that function equal to 0.5 if I were trying to find like a median value, because that's like the 50th percentile, right? So the way that I would run this one is, again, I'm going to come over here, I'm going to turn this into 1/3 x squiggly cubed plus 2x squiggle, evaluated from x to 0. And again, the nice thing is, and I'll write this one out this time, we turn that into 1/3 x cubed plus 2x minus 1/3 0 cubed plus 2 times 0. The nice thing is that one goes away, but you can see now that because earlier, you know, as long as this is a valid PDF, it is technically a definite integral. And so I don't have to like add a constant or anything. I just go over the bounds and I treat the upper bound as this little x thing here. Nothing too crazy, nothing too wild here. This turns into f of x, right? And you can see if I had used k within the PDF to shrink, that would affect this f of x, this big f of x, this CDF of x. But if I used k in the domain as the upper bound of the domain, it actually doesn't affect it, which is pretty funky. It's pretty cool, pretty nifty, if you will. This f of x will have the same domain, though. This is still from 0 to k, whatever that k ended up being, right? Yes? Mm-hmm. Yeah, like I was saying with Jed, we will give you a k here or a k here. Like, it'll be clear. You've just never done it before. So, just wanted to show you. Functionally, same deal. Tyler.
So just double check. When we have the k in the bound, we'll just solve for k as usual, and then that k number will go from 0 to
Yeah, or from whatever number to whatever upper bound we give you. Like, it could be a lower bound too, right? Yeah.
What would be the purpose of like restricting the bound to like k?
Maybe I really like the function x squared plus 2 for some mathematical bias reason or something like that. It gives me a cool expected value that's useful for later. Something like that.
It's like if you're like altering the length of that domain and you're trying to find probabilities, it's probably going to be different than before.
No, not necessarily.
For example, if k is 1/2,
Yeah.
and I say what's the probability of I get 1/2, and you're treating the domain to 0 to 1/2, it's going to get 100%. But
Yeah.
before it wasn't 100%.
Well, the thing is, like, before we can't consider that because before it wasn't a valid PDF. Like, until we solve for the k, none of the probabilities we look at are valid because they're either representing less than or more than 100% of total possible outcomes. So with this PDF that I've written up here, if this is the true PDF that I'm working with, and my bounds are too wide, this PDF is going to give me bad numbers, which is why we adjust with k either in the equation itself, or if I really like the equation, we just adjust the bounds. So there's that one. I think we're going to be chill on PDF to CDF there. That's the homework key. Let's just keep track of our progress here. So we've got go from PDF to CDF. And you guys remember, if I want the probability of something, I can, well, we just went over it. Integrate the PDF over the bounds that you'd like, or just plug it into the CDF. Anything you want to do. Make PDFs valid, covered. Let's talk about marginal PDFs for a second, and joint PDFs. Because again, this K thing, totally valid if you had two variables, right? If I had a function that looked like, if my function instead looked like x squared plus 2y, and maybe x is an element of 0 to k, and y is an element of like k to 6 or something like that. Again, same process here. This one would be a little bit more obnoxious algebraically, but you're just going to do the same double integral you've been doing before, set it equal to 1, solve for what k needs to be, right? So you'd integrate y from k to 6, and then you'd integrate x from 0 to k, or vice versa. The order doesn't matter, which is nice. It's a nice little calculus thing. Whichever one's easier is the one you'd want to do first, right? That's what we're going to deal with. Like, again, you can do this with a joint PDF. Now, the nice thing to have done would have been if I had come up with a valid like joint PDF. I think I remember one as being 1/3 1 minus xy from like the homework. Is that right? I can actually go check really quick. Let's just go pull this one up really quick. Oh no, it's 4/3. That's what it is. So we know from one of the homeworks that a valid joint PDF, which I'll call a JPDF, just joint because it has multiple variables interacting with each other, was equal to, yeah. I just tried to write 4 as the word, so that was fun. 4/3 minus 4/3 xy. Again, not to put too fine, oh, and the bounds. I was looking for the bounds, yeah. Where x and y are both elements of the set, the continuum, 0 to 1, right? They're between 0 and 1. Again, not to put too fine a point on things, but you guys can tell, probably, that 4/3 is kind of like a k here, and the really nice function was like 1 minus xy. I don't know if you've noticed that, but if we were to shrink that xy domain, that 4/3 would have to change, potentially, right? Or vice versa. Who knows, right? Anyway, let's get a marginal probability density function. If I would like to know, if I hold y constant, what happens to x? What does x look like? Then what I need to do is I need to integrate y out of the equation. If I want the marginal probability density function of x, which we've called fx of x, I need to like account for all of the y's and all the ways that y interacts with x over the entire bound of y. So all I do is I just integrate y out of the equation, right? 4/3 minus 4/3 xy dy. That turns into 4/3 y minus, what was it? This should be 2/3 xy squared, evaluated from 1 to 0. And I trust that you can see that when I plug in 1 for y here and subtract when I plug in 0 for y, it's going to turn into 4/3 minus 2/3 x. We can see that, right? Yes, no, maybe so. Excellent. This is the marginal probability density function of x. What that means is, if I'm not looking at y at all, what does it just look like when I only look at x? This is what it looks like, which is pretty cool. If I were to make a rough graph of what this PDF looks like over the bound from 0 to 1, let's call that 1. Here's x. Here's fx of x. It will intercept, right? Here's 1. We'll call that 4/3. And it will kind of come down like this, right? In fact, it will come down a little bit steeper. That's basically what that looks like. And the fun fact is, because we know this is a valid PDF, this integrates to 1, which is pretty cool. I'll leave that as an exercise if you want to verify that. Anyway, let's say, for example, now that I have this marginal probability of x, this represents the probability of a given x value in terms of the math. Not literally, not technically, but in terms of the math. So what if I wanted to know, like, what is like the probability In fact, what if I wanted to know, like, if x is 1, we're at the far end of x, then on average, what is y? Because, like, we have this joint PDF at the top. X and y interact with each other. They don't always pull out the same. You know, the same outcome doesn't always happen. But what do I expect to happen to y if I set x to 1? Like, if I just make x 1, in that universe where x is 1, what does y usually look like? Well, what that could look like, I'm going to get rid of this work here. I'm going to just keep this up here as fx of x. Okay, just keep that up here. Well, what if I want to know, you know, what does y usually look like in the universe where x is equal to 1? Okay? You recognize this. This is a conditional probability. You've been doing these since, like, lecture 7? No. Lecture 14? That's a big gap. But you recognize that the formula for a conditional probability is, of course, the probability of A intersect B over the probability of B if you're doing, you know, the probability of A given B, right? We all remember that. We recognize that, right? But how do you translate that into these PDFs where it's not P anymore, it's F? Well, the thing to remember is that these Fs, these lowercase f's, functionally, for continuous functions, represent, in this formula, those P's. And in fact, let me point out to you, really quick, the generic form of the conditional PDF. The expected value of y, given that I set x to some random value that x could be set to, is equal to the probability, and in fact, let me make that x blue just to be explicit about it, right? That x is equal to some set value of x. This is the probability of seeing that specific x with any y over the marginal probability of seeing that x. Which is to say, if I live in the universe where I have always set x to blue value, what does y look like? What is the probability? And in fact, you'll recognize that this is not the formula for E, this is the formula for P. Unfortunately. Well, I'll get back to E in a second, and I'll show you why that was silly. But right now, the thing to keep in mind is that the probability of seeing any given y, given that you fixed x to blue, right, could be anywhere within the bounds of x, is this conditional probability formula, because the joint PDF represents the probability of the intersect, right? If I look at both of them at the same time, what's the probability of seeing this and this? Blue x and any y, right? Once I solve this out and I actually plug in a value for blue x, this will turn explicitly into a function of y and only y. Because again, what is the probability of y when I have fixed x at some number value? I'll show you. We'll do that right now. We'll go back to what I did before, right? What is the probability of y? Or in this case, you could say fy of y, given that x is equal to 1. That might be a little bit confusing, so normally we just leave that y off, right? Because this is not technically a marginal probability. This is a conditional probability. But it will only be a function of y. Let's show you why. On the top of the fraction, I have f of x and y. But in this case, it's not f of x and y anymore. It's f of 1 and y. Over, normally, fx of x. But in this case, I've fixed x at 1. So let's plug that in. On the top, I have 4/3 minus 4/3 xy, but I'm plugging in 1 for x. So on the top, I have 4/3 minus 4/3 1y. Over, on the bottom, I'm plugging 1 into this fx of x, which means on the bottom, I get 4/3 minus 2/3 times 1. I solve that out. On the top, I have 4/3 minus 4/3 y. On the bottom, I will have just 2/3. I trust that you can see that. Dividing by a fraction is the same as multiplying by its reciprocal. So let me put 3/2 over here. Everybody follow that? Makes sense? Okay. I solve that out. These 3's are going to cancel everywhere. These 2's are going to cancel 4's. This f of y, given that x is equal to 1, is equal to 2 minus 2y. Yes, no, maybe so? And that is still over the bounds 0 to 1 for y. Okay, we've not changed the domain at all. All that we've done is we've accounted for the fact that usually when x is high, y is also high in this distribution, or maybe low. I can't actually tell, honestly. But this is what you've got. This is the conditional PDF here. And you saw that we got it by just basically modifying that Bayes' theorem equation, where we had, the probability of A intersect B over the just the probability of B in general, right? We see the probability of the value that I'm plugging in with the one that I want to leave arbitrary, in this case y, over a set environment where I have fixed, I know everything that's going to happen in this new 100%, this new environment where x is only ever equal to 1. I know exactly how I need to scale stuff, so on and so forth. Okay. Let's take a look at this. That will cover that, which is great. Do we cover anything else by talking about this? We have yet to do so. That's fine. Any questions up to this point? Yes, no, maybe so. Excellent. Yes, Jed.
What cases do we do that but integrate?
What cases do we do that but integrate? Oh, yeah. Absolutely. If I wanted to know the expected value of this,
you do it with respect to, you integrate with another y.
Yeah, so I would take this function, I would multiply it by whatever's in the parentheses, in this case just y. Once you've built this conditional probability function, by the way, you'll continue to write like conditioned on x equals 1 or given x equals 1. Like when I write e of y given that x is equal to 1, I'll continue to write that, but after I've just got the function 2 minus 2y, I don't have to worry about it anymore. I've already built it into the function. Okay? So yes, what I would do if I wanted to take the e value here is I would just do the integral over the bounds of y, 0 to 1, of y times the probability of y, or, not to put too fine a point on it, but the integral over the bounds of the thing times the probability of that thing, right? Y times, in this case, 2 minus 2y dy. That would be equal to the expected value of y, given that x is equal to 1. Easy peasy, good stuff, right? Yes, no, maybe so? If I wanted the expected value of y squared, maybe, then I just square y here. I don't actually do it in the function. So, another thing to keep in mind. The thing times the probability of that thing over the bounds of the thing. Super clear and super simple, right? Easy. You're gonna blow it out of the water in the test. Okay. That should cover everything there. Let's talk about the formulas for beta hat 1 and beta hat not. And I'm gonna be honest with you, I don't remember what they are. So here's what I'm going to give you. I know that beta hat not, maybe I actually do remember these. And on the test, if you see, so actually here's the thing. In my heart of hearts, in my beautiful, wonderful, pondering soul, some people, instead of writing y is equal to beta hat not plus beta hat 1x plus some error term, some beautiful, wonderful, incredible people in this big old world of worlds might write xb is equal to a plus b times xa plus some error term. This second one you'll never see again. So it boggles my mind and heart why some people who will not be named choose to notate this like this, right? No idea. personally. However, the thing I would like to point out, beta hat naught and A are both intercepts in slope-intercept form. And beta hat 1 and B are both slopes in slope-intercept form. So as I'm going through this, I'm going to use beta hat 1 and beta hat naught, but please keep in mind that no matter how you notate it, you could write, instead of A and B, you could write star and cube. The formula for beta hat naught is the intercept formula. The formula for beta hat 1 is the slope formula of a basic single variable regression. So please keep that in mind. With that in mind, we can put these up at the top here. Now the one that I do remember, and hopefully one of you can pull out your notes and get me the formula for beta hat 1, but the formula for beta hat naught, I do remember as being y bar minus beta hat 1 x bar. It's just the difference in means, which is nice. Now, whoever gets this first is actually going to get a bonus 6 points on the test, so definitely someone wise would be looking for that equation right now. Tyler might have it. This will probably be an equation for B in your notes. Hit me, Tyler.
It's either sigma xy.
That's the one.
Sigma x
There it is.
Or sigma y over sigma.
Yep. So we've either got the covariance of x and y over the variance of x, or we have rho, the correlation, times sigma y over sigma x. Yes? No? Maybe so? One thing I would like to point out to you that I think is pretty nifty is if I expand rho into the actual formula for rho, you'll recall that that is the covariance of x and y over sigma x, sigma y. If I were to multiply that by sigma y over sigma x, it does not take any large struggle of the imagination to see these two canceling them out and these two becoming sigma squared x, right? So hopefully that will show you why these two formulas are equivalent. Now, in what case do you use which formula? Well, let me suggest to you that if we give you rho and the two standard deviations, that you use the formula that has rho and the two standard deviations. And if we give you the covariance and the variance of x, that maybe you should use that formula instead. Just a suggestion, no real reason behind that one, but don't try to use formulas that you don't have the pieces for, is generally a solid strategy. One thing that this does bring up is the opportunity to review the actual formulas for sigma xy, sigma x squared. You will recall, of course, that sigma xy is equal to the expected value of xy minus the expected value of x times the expected value of y. One other thing I would, of course, like to point out to you is that what if I set this y equal to x? Well, the cool thing is that would make this sigma into sigma xx, which is just sigma x squared, right? Sigma squared of x. That would just be the expected value of x times x, or the expected value of x squared, minus the expected value of x times the expected value of x, or the squared expected value of x. Bless you. Yes, no, maybe so. Makes sense. These are the same formula. Just one of them has a y and the other one has a second x. Right? Isn't that nifty? Isn't that fun? Isn't that cool? I don't know. I think it's pretty nifty. Yeah. So, and then of course, if I want to go from sigma squared x to just sigma x, I just square root sigma squared of x, which has its formula right there. So, nothing crazy. Nothing you guys don't know how to do, because again, these e's here, you know how to do that. It's just the thing times the probability of the thing, and you add up all of those, be it via an integral or by just adding them up in general, right? Say, for example, right, and we'll come back to beta naught and beta 1, right? But beta, Beta naught and beta 1 are super easy. If you could just remember the formula, these formulas right here, and I don't even remember, like we might even give them to you. That's a thing to check. Just check the document that's on Learning Suite that has all the distributions and the estimators on it. And if we give you these formulas, don't memorize them. If we don't give you those formulas, you probably maybe should consider memorizing them, potentially. It may show up on the test. I don't know. I'd have to ponder a little bit more on that one, personally. But, but the one thing that you do know how to do is like this E of something, right? Say, for example, you were given like revenue in a table, and we have like a store or like a copper mine or something like that. I don't know. We have day 1, day 2, day 3, and in day 1 we made 100 buckaroo. Well, it looks like we made 105 buckaroos. And then on day 2 we made 100 buckaroos. And maybe on day 3 we made, I don't know, 95 bucks, you know? And you'd look at that and you go, okay, I'm going to do the expected value of revenue. And because I have such a great TA who has beat this into my head so many times through the semester, I know that if I want the expected value of revenue, I just take the thing, which is going to be revenue, times the probability of the thing, and I'm just going to add those up. But wait, what the fetch is the probability of the thing? He never told me that. Well, you won't be able to say that because I'm telling you now that if you get something like days or weeks or months or something like that. Oh, there's a lot of people in the chat here. Why is my computer not charging, actually?
There's a lot of one person.
A lot of one person. This is actually bad. I need this to charge. I don't know why it's not charging.
It does outlets there on the actual stuff.
Oh, okay.
That one's good.
Oh, okay, that's fine. It's good that I caught that before it actually like died. Good, there we go. That would have been really bad. What are we seeing in the chat? PDFs, ECON. Oh, it's just chat. Sam, drop a super chat. Bet you won't. Anyway, the thing to put out. This is why this is great, man. I love streaming, man. The energy's just so high. It's so hype. You never know what's going to happen. Let's get back to where I was pointing. Is if you have 3 days, what is the individual likelihood if I took those 3 days and put them in a hat, what's the chance of pulling day 2? It's a third, all right? If I've got 7 days and I throw one of them into a hat, if I throw them into a hat, the chance of pulling each one out is 1/7. So if you see a table like this and they say, please find the expected value of revenue, it's just average revenue over the 3 days, right? And then if you need to find the expected value of X squared, just square the revenues and then average that, right? The formula for the expected value, that's the thing times the probability of the thing, add up all of those. In this case, the probabilities are all implicitly 1/n. Just however many days there are, throw them in, and you're good to go, okay? So, I won't run through that problem with you, although you may want to consider doing something like this for just, I'm feeling it, you know? That's what the vibes are suggesting, potentially. Check that out. How do I don't... I actually don't think you can. I don't think I have it set up, which is probably for the best for a number of reasons. Anyway. One what? One. Wait, one. Oh. Let's go! Yo, this engagement is really going to drive traffic to my channel, you guys. Thanks so much for watching. Be sure to smash that like button. Okay, let's go back to our checklist to make sure that we're checking some stuff off, right? Okay. So you have the formulas for beta hat 1 and beta hat naught now. I'm not going to like go through like finding those, because the parts of them are things you already know how to find. All right, just remember the formula if it's not on the sheet, and if it is on the sheet, don't even remember it. Just know what sigma y is, and like know what rho is, stuff like that. Yes, Tyler, hit me. R squared. Well, so like rho squared, right? It's just rho squared. What is R squared, or what is rho squared? Well, rho is like a correlation thing, right? And it says if I move this by 1 standard deviation, I move this by this many standard deviations. Negative 0.2, negative 0.8, maybe 0.75 standard deviations of the second thing. Who knows? But that goes both ways. And so if I square rho, what that gives me is the percentage of variance in the 1, the outcome variable, the y, that is explained by variance in the x. Hit me, Jed.
Why do we use variance when it seems like standard deviation is a much more like useful than like?
Do you just mean in that definition of rho squared there that I gave you, or just like in general?
Just like in general, like it seems like variance is very like vague and undefined, but standard deviation is very.
Standard deviation is also pretty vague and undefined. Like the best thing we have for standard deviation is that like most of your observations are going to fall within plus or minus 2 standard deviations of the average, which in itself doesn't actually, like if you think about it, it doesn't really tell you that much about what a standard deviation is.
True.
Right? So, and the only reason we have that plus or minus 2 rule is because of 1.96 on like the normal table, right?
Right.
So like, again, this is just, it's an arbitrary thing. The reason that we use variance, standard deviation, any of this at all is actually just the underlying math. That's it. The math, the formula of expected value has these cool properties that lets us do all of these things. Bro. Bro, am I gonna have to, oh, Braden's in there too? Let me know if it gets distracting and I will actually block them. No, I'm just kidding. I wouldn't. Well, I would. I would do that, but I don't think I will. I think it's fun. I think it's fun and funky. I also would like you guys to know, if you have to leave at any point, like feel free to. This will probably run a little bit longer than the 10:45 when we usually get out, especially at this pace. But yeah. So we just covered getting E and V from time series. And by time series, all I mean is like if you have equal probabilities between things and we don't tell you, hey, the probability of day 3 is 33%, right? So keep that in mind. Formulas for E and V, you guys know. All right, I'm just gonna, you just know those. V is, I actually also just gave them to you, so that's pretty cool. Correlation and covariance, you guys should also know. I mean, I gave you the covariance one there, and I also did something with the correlation formula when I, parsed out beta 1, so you should be able to go back and review that. And if at this point I need to review for you like how to find covariance, it's going to be a little rough for you on the final, not going to lie, but I trust that you guys are all in a better place than that. It's like the beginning of Alma 7 when he's just coming from Zarahemla. And he's like, Zarahemla sucked, but I trust that you guys are better. I trust you're more prepared for me here. And he was right in Gideon. Anyway, let's see. Conditional probability formula, we did that, kind of. Percentiles, we've talked about them. Can I just suggest to you really quick that a percentile is a value on a PDF such that the percentile n, right? So the nth percentile value of a probability distribution function is the value of that function such that n% of all the other possible values from that PDF are smaller than it, or to the left, or more negative than.
Would that ever change if your graph is, so like for example, on some of the tables, you integrate from the right to the left?
Yeah, so even on the chi-squared table, that still applies. Reason being, like, let me draw a graph that looks like this, and let me draw a graph that looks like this. We'll call that 0, right? That's a really that's a very symmetric graph right there. Okay, where is the 50th percentile of each of these graphs? Well, the 50th percentile value is the value of the PDF such that 50% of all possible values of that PDF are more negative or to the left of that value. So if I am symmetric around 0, that means implicitly my 50th percentile, or my median, is 0. Yes? Let's say, for the sake of argument, that the 50th percentile value on this distribution is right here. That's probably not a great illustration. But let's say it's like right here. Because this goes out forever, but this one stops at 0, right? So let's say, for the sake of argument, that this is 50% of the distribution, of the area under the distribution is lying right there. Whatever this value is, let's say it's a chi-squared, potentially. It is a value that has 50% to the left of it. 50% is a bad example here because it's symmetric, so I also have 50% to the right. But let's say, for example, that instead of being 50% up here, this is actually 60% of the chi-squared distribution. And here's a chi-squared score. First question is, what is the alpha on this number going to be on your chart? Like, this one isn't on your chart technically, but if it were on your chart, what would the alpha on this chi-squared value be? It'd be 0.4. Absolutely. Because you have 0.4 to the right, and that's how the chart is highlighted in. But the question is, what percentile value of this particular chi-squared distribution is that number? It's the 60th percentile, because the definition of percentile doesn't change. Okay? Keep that in mind. That was a question on a recent homework, I remember. Threw some people off. I'm going to be... When does that show up? Does that show up on the test? Well, I wouldn't know. I haven't seen the test. So, but I'm pretty sure it shows up if I were to have written the test and looked at it and knew it was on there, potentially. But alas, I am left to ponder in my heart of hearts. So, is that joke kind of wearing off? Well, what can you do? Might as well beat a dead horse, right? While we're here. That's good for percentiles. Confidence intervals, hypothesis. Man, I haven't even done any of the best parts of the review. Let me just cross a couple things off of here really quick. If you need to increase your confidence interval, if you need to increase your confidence level, you need to make your interval wider. You need to capture more possible values if you want to be sure that the real value is in your net. Okay? That's just a basic one. Easy peasy. We'll get to that one. The law of large numbers suggests what? Okay, yeah, sorry, my bad. Law of large numbers says... Well, so central limit theorem is different, right? Central limit theorem says that every distribution, that's a sample. Like, if you keep taking samples from a distribution, eventually those samples will be distributed normally, right? That's what CLT says. And some of you got tripped up on the test because that applies to any distribution, not just the continuous ones. And we can chalk that up to wording or whatever as well. The law of large numbers suggests that the average of your sample will approach the true mean, right? Slightly different things. CLT has to do with the distributions, and that the distribution of X bar approaches normal, standard normal, in fact. Well, not standard normal, but normal so that you can standardize it, standard normal. The law of large numbers suggests that the bigger your sample is, the closer your... it's basically what makes X bar a good estimator of the true population mean. That's all it is. That's all you're really going to need to know about those two things, if I had written the test.
Question.
Yep.
So as n goes to infinity and any sample of n goes to infinity turns into a normal distribution, the mean of that normal distribution is not necessarily the true mean. Is that how they differ in definition?
No, so we know that like X bar is distributed as a normal random variable with mean mu and variance sigma squared over n, right? Like that's just something we've covered a couple of different times. The reason that this mu is here is because of the law of large numbers. because 1 over n times the sum of, you know, xi, whatever. Law of large numbers tells me that approaches mu, right? As n approaches infinity, which is pretty cool.
And kind of my question is,
Yeah.
for CLT,
Yeah.
as the random sample approaches infinity and that distribution approaches a normal distribution, will the mean of that distribution that has now been normalized, which was one sample, will it also have its mean approaching the true mean, like the law of large numbers?
So the question is creating a false dichotomy. This is LOLN, law of large numbers over here. This is CLT. These are the facts. That's all it is. Like, law of large numbers is part of the CLT. It's this part right there.
Thanks.
Cool. Good. Excellent. Now, I haven't even gotten to go over my fun ways to think about hypothesis testing with you guys. I think we'll do that in these 15 minutes, and I think I can make that work, actually, which is really nice. So, in terms of Stata, just, if you want to go into Stata and open up the help gen, and just look at where the equals and the double equals are, like from the assignments. Just do that, okay? The generate command needs one equal sign. You do generate, the name of the variable, one equal sign, and then you could do a value or you could do a logical expression. Just go back over that from the assignment. You'll have a good time with that. That will cover everything you need to know. And as long as you know how to read a help file, you'll be good to go. I will show that at the very end after I cover the important stuff, but that will probably come after 10:45, and I want to get through the crunch of like hypothesis tests and like confidence intervals and all that stuff before you guys have to, like, before my time is over. Right. So we will cover all the rest of that stuff. The one other thing I need to get for you really quick is just the idea of an event tree. If I have, let's say, you know, 3 coins, and then like, so these are little coins right here, and I were to say, okay, I pick a coin at random to flip, and then I flip it, right? You would say, okay, I start here, here I am, and I can pick, you know, let's call them coin 1, 2, 3. I can pick to flip coin 1, 1, 2, and 3. In fact, let me just write 1, 2, 3. And if I pick them randomly, what's the probability on each of those branches? It's a third, right? And I'll label the probabilities with a different color. 1/3, 1/3, 1/3. And then each of those coins has 2 outcomes, right? What are the 2 outcomes? Heads or tails, right? Let's say, and those are also random, so they're like 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. But what if I told you that like coin number 3 is actually weighted so that it has a 75% chance of being heads, right? Then what is the overall chance of flipping heads? Well, the first thing I need to do is I need to come into my event tree. I need to change this from 1/2, 1/2 to 3/4, 1/4 on the 3 branch, right? I'll say, if you pick the 3rd coin, there is no longer a 1/2 chance that you get a heads, right? It's a 3/4 to get a heads, but that's from the 1/3. So the question is, what is the overall probability of getting heads? Well, that is right here, plus right here, plus right here. You need to multiply through the branches, so it's 1/3 times 1/2, right? 1/3, 1/2, 1/3, 1/2, 1/3, 3/4. 1/3, 1/2 plus 1/3, 1/2 plus 1/3, 3/4. That's going to be equal to a 1/4 plus 2/6, so a 1/4 plus a 1/3. That's 3/12 plus 4/12 is equal to 7/12. Okay? Does that make sense? I think it does, because there are, you know, there's only 6 outcomes right here, but this has scaled us off of those 1/2s. So there are kind of like 12 potential world outcomes just because this is divided further in half. But anyway, you are going to need to think critically through an event tree on the test. That is a question that I wrote. Think carefully about the first branch, the second branch, and the third branch. The first branch will be, I'm just going to give you a little hint right now. The first branch will be something you pick. The second branch will be something someone else picks. No. The first branch will be something you pick. The second branch will be random. And the third branch will be something someone else picks. Keep that in mind. You'll see when you take it. I think it'll be a pretty, I kind of wrote it to try to be a kind of easy question. I think it's more going to be a fun one, I hope. I hope you have fun with that question. Especially you, Kalel. I hope you really enjoy that question. And you guys are going to know once you sit down and write this, but the amount of time it took me to actually figure out the math and like question, but the amount of time it took me to like actually figure out the math and like what to ask you guys was so annoying. But it's fine. It's going to be a great question. You're going to be super well prepared. Just think carefully about each branch of an event tree. Later, Brenna. Or are you coming back? You're just filling up your water. Okay. Cool.
Because of that, like, game show type
No, definitely not. No, it definitely couldn't be that. Absolutely not. It's definitely not about the Monty Hall problem. So keep that in mind. If you guys want to take a look at that.
I know what you believe, and I'm going to put that.
See, it's not a belief though, and that's what you'll get. And that's the great part, is that like if that question shows up on the test, you're going to be like, oh, there's the math. It'll be great. No, but it's not on the test. Don't worry. It's definitely not on there. Definitely don't look that up. Anyway. I've said too much. Nah, it's okay. We're chilling. CLT, conditional lettuce tomato. The fetch. Anyway. What if I like made this joke about it like being about that and then it's just like not there? Like what would you even do? Just be like, where is it? Can you imagine? That would be so fun. Just completely psyching you guys out. Imagine. Am I the kind of guy who would do that to you guys? I can't believe I would do that. No, I couldn't have that in my heart of hearts to do. Anyway, let's actually get into the important stuff really quick, which is the idea of hypothesis testing. We have 10 minutes. You've had this lecture probably 3 times now. Means, chi-squared variances, standard deviations, proportions, difference of means. Like that's 4 different versions of this lecture that you've had. So all I'm going to do is I'm going to give you the way that I finally figured out to like consistently think about these kinds of questions. Let's say, for the sake of argument, that I'm a high-level CEO at an airline company. And my airline company is called, also I think this is the example I used in the final review from last semester, but my flight company is called 5 minute, or it's 5 or fewer flights. What does that mean? Well, as a company, I built my company so that we can make the claim. And in fact, I've staked my entire reputation as a CEO on the fact that the average wait time, the average delay time of flights in my company, in my airline, is 5 minutes or less. It's never over 5. Okay? Or just on average, it's 5 or few. It's 5 or less. Okay? That's what I have staked my reputation. I built this company from the ground up with my bare hands and by my bootstraps and American grit. But I have hired this intern out of some dumb university like Brigham Young University or something like that. And he goes, you know, boss, I took a stats class once called ECON 378, Statistics for Economists. I'm like, never heard of it. And he says to me, or she, probably she, no, probably he, because he's kind of dumb. I don't like him. And this intern, he just walks up to me like, I'm the CEO. And he goes, you know, boss, I've actually been running some stats, and I don't think that like 5 or fewer makes sense anymore. Like our average flight times, I think, are like higher than that. Like I took some samples, right? And he comes up to me, and this intern tells me that he took a look at, like 80 different flights across the company. I'm like, that's cool, that's great. right? And he told me the following information. He said, you know, boss, I took a look at 80 flights. And in fact, let's actually make it 8,000 flights. He's been an intern for a while. He doesn't really have that much to do because I made the company really nice, right? And he told me that the average delay across all of these flights is actually 5.1 minutes, which is not fewer than 5. And I'm like, dude, can't you read? Like, it's 5 or fewer flights. Come on, let's chill for a second, right? And he goes, but boss, check this out, right? He tells me that the sample standard deviation across his entire sample is like 0.2 minutes, which is like 1/5 of a minute. So it's what, like 12 minutes? Or no, 1/5 of a minute. 12 seconds. Yeah, there we go. I don't know how he timed these so precisely, but what can you do, right? That's his sample standard deviation. I'm like, cool, right? And he says, boss, I think we need to rename the company. And I go, bro, how long have you worked here? He goes, like 6 months. And I go, bro, I built this company from like the ground up with this as my vision, right? Like, do you know how much it would cost me to change all of the paint jobs on the airplanes and the branding in our airports and like our commercials that we run on TV? Like, do you know how much that would cost me to change? Like I would not even ever consider doing that unless the probability of you actually being right and me being wrong was like greater than 99%, right? I'm like, that would be super costly. And you can see where I'm getting that alpha from, right? Okay. What's my null hypothesis here, by the way? Someone tell me what the null hypothesis is.
It shows that your mean is 5.
Mean is 5.
Or less.
Yeah, 5 or less. And we'll talk about that in a second. What is the alternate hypothesis here? That it's greater than 5. So implicit in a one-sided alternate hypothesis, is this frozen? No, it's just taking a second. It's just a little slow. Implicit in a one-tailed alternate hypothesis, like a greater or a less than, is that in the null is the other side of it. We just write equals because you're never going to plug in like a less than or equal to into test statistics. It's nice to just keep it as equals. Just keep in mind, right? Yep. Two-sided, we'll talk about that in a second, but yes. Basically, the idea is like implicit in this h0 that we have up here is mu is less than or equal to 5 because the alternative hypothesis is only is greater than. If this were just is not equal to 5, then, I mean, it's just mu equals, and so we just keep it consistent, right? So here's what I'm going to recommend to you guys doing, okay? I'm just going to show you how I would solve this, how I would write it on my paper, how I would avoid getting confused, okay? Also, if you follow this format on the test, it's going to make it like so easy for me to grade. It would be awesome if I were the actual one grading it, which who knows, honestly. I draw a little dotted line over here, and on the left side, I say test, stat. And on the right side, I say crit val. Critical value, test statistic, if you will. I don't touch the left side yet. Wow, this is really behind. That sucks. Well, you'll see it in a second anyway. I'll just have to draw stuff before I'm explaining it, so I can actually do that. So you can see I've got on these two sides, test statistic and critical value. Now, because I have an S here and, you know, an X bar, and I'm doing a mean hypothesis test, I'm going to be looking at a t-table, right? But notice that we're at like 8,000 on n. Like that's well beyond the range of the t-table. And at that point, you just treat it as the normal table, okay? So that's what we're going to be running with. So I'm going to use the z-table. It's centered at 0. And I need to pick a value on the z-table such that, in fact, I'll change this to a different color. I need to pick a z-score such that the probability of being to the right of that score is equal to what? Is equal to, oh, to the left, yeah, 99, absolutely. I meant to say to the right, but you're correct. It is 0.99 to the left because this is a greater than hypothesis test. Wherever I'm rejecting something, is going to have to follow H1, right? So like we can see up there, my rejection region is I need to pick this Z up here such that, you know, if my test statistic falls to the right of it, I know that the test statistic only had like a 1% or lower chance of falling to the right of that value if H0 is true, which means I will say H1 is probably true, right? So then I just pull up the table, and I would pull up that value, right? And you guys can go to the table and pull it up. You know, with the 99 there and the 1 there, and you have your table, that once you standardize, you'll know how to pick that value at this point, right? You pull up the table, you go to the center of the Z table, which is where the probabilities are. We covered this in the last midterm review as well, as we covered how to read these tables. So if you need to, you can go back and watch. It's on here, right? It's on the channel. You know how to get there. I'm just going to tell you that that value is 2.32, because that's what it is. Fun fact. So now I have a critical value, and I'm just going to leave it there. Now I'm going to jump back over to the test statistics side. And we, of course, remember that the test statistics that we're going to use, we all remember the formula for this test statistic. In fact, as it's showing up on the screen, hopefully pretty soon. We're going to be using like standard normal because we figured out that n is kind of huge here. The formula is x minus mu over s squared over the square root of s squared over n, right? Or just s over the square root of n. That works too, right? We say that that's approximately normal distributed if n is big. We know that it's distributed as t if n is small, right? Just keep that in mind for the test. Also, if you're confused about which one to use, if you just write which one you're using and why you're using it, if you're doing it for good reasons, I'll give you points either way. Just as long as you know why and can tell me why, you're good to go, okay? Just keep that in mind. I'm going to plug in the numbers here. Turns into 5.1 minus 5 over the square root of 0.2 over 8,000. In fact, it's 0.2 squared. I'm just going to pull out my calculator here, and you'll see this in a second. I don't know why it's taking so long. It wasn't taking this long the whole time, was it? Yeah, okay. That's just funky. I'll just have to figure that out. It's probably just a computer thing. But anyway, I'm going to start writing these numbers in. And this is the nice thing about getting an iPad, for any of you guys who don't, is this application right here, the MyScript calculator, is kind of broken. It's kind of cracked. It's actually crazy. And you're going to see in a second, I won't spoil the surprise, but any guess as to whether we're going to reject the null hypothesis or not, just kind of based on these numbers? Yeah, we're definitely going to be rejecting, as you'll see here. That number is enormous, right? So, but I'm going to keep to the example, right? So I find that answer, and I'll come back over here and I'll say it's the test statistic I found is like 44.7. And then all I'm testing is I take the critical value that I found, and I take this test statistic that I've got, and I put a question mark between them, and I say, is my test statistic more extreme than my critical value? Which is to say, if the null hypothesis, or if the alternate hypothesis is a greater than hypothesis, is my test statistic greater than my critical value? If it's a less than alternate hypothesis, I say, is my test statistic more negative, more extreme, smaller than my critical value, right? And it's all based on that drawing that I made over there to the right. Now, clearly, in this case, like obviously, we are rejecting this, right? And if I asked you, if on the test you were asked to find the p-value of a z-score of 44, that's not on your chart. I don't know if you've noticed, but it is well off of the bounds of your chart. So you would say, for all intents and purposes, it is 0, right? As long as you can recognize, hey, it's not technically 0, like there is technically still like a p-value to that, but it's so small that it's practically 0, right? Just let me know that you know that, you'd get full points. Now, I'm pretty sure we don't ask you to do that on the test because asking you to find the p-value of a 44.7 z-score would be absurd. Let's actually take a look at what this would look like if there were only 80 observations. Again, this is probably entering into t-table territory, right? But for the sake of this, let's just keep doing it normal, right? What does this number look like if I've only got 80 observations? That's a little bit more sensible now, right? That's still well within the rejection region, though. What I'm trying to get across to you is if you set up the problem with this like two-sided thing, where on the right you draw a table, and you use the table that you draw to compare to the tables that you are given. If you draw it correctly, just over there on the right, and you pick the value, and you do that little underline thing where you like, I need this % of the probability here, and I need this much of the probability here. If you could do that, you will never like get confused between chi-squared and z and t, which is nice, right? So then you can just come over to the test stat, and even if it's n-1 s squared over sigma squared, right? These are all things you'll have on that last paper of estimators and distributions, and it's past 10:45, so if you need to go, feel free. This is pretty much the last thing. Then just calculate your test statistic. Put all of the work on the right side into finding the correct critical value, and then just plug numbers into the test stat and look at them. That's all you have to do. And if I ask you to find a p-value, it will be a value that's on the table, but you will know how to find the p-value because you can just write the number onto the little graph that you drew on the critical values side. First of all, you'll be able to tell whether you fall in the rejection region or not. Take this 44.7 and put it on the chart, right? 44.7, or like a 4.7 in a realer world, or like a 0.47 if there were fewer, you know, potentially. Or if the numbers were slightly different, and those will show up in a second, unfortunately. But basically, split it up, critical value, go to the chart, draw the graph, find the number, draw the little percentile, like the percent of the graph under the curve to the left and to the right, or to the left, to the right, and in the middle, depending on if it's two-sided, right? Draw those out, pick the right value. You can do that. You know how to do that. You actually knew how to do that before the most recent midterm. If you need help remembering how to do that, you go watch that video, right? Put that 2.32 down. Don't touch it. Go to the left. Fill in the numbers for the test statistic. Get that number. Compare them. That's it. That's all it comes down to. And then, if I ask you for a p-value, recognize that the alpha of the critical value is the p-value of the critical value. So then the p-value of the test statistic is just going to be in whatever direction the alpha went, it's that. But instead of for the critical value 2.32, it's whatever it is for 44.7 or 0.47 or 1.6 or whatever it actually ends up being. If you could just keep it straight like that, you actually have everything you need from this. The one other thing that I will point out to you is if I wanted to create a 99% confidence interval in this case, or in this case, a 98% confidence interval, I can take this 2.32 right here, and it's going to take a second to show up, but I can take this 2.32 right here, and I can get the negative version, and then I can just do x bar plus or minus 2.32 times whatever these numbers were, you know, 80, 8,000, whatever it is. Just take that. Wow, it's really taking a long time. That's so odd. Anyway, just take those two things, plug in the plus and the minus, create the confidence interval. That's all you got to do. If we were to ask you to do that as chi-squared, you don't get to do the plus and minus, but the point is still the same. You just pick those two values, add, subtract. Easy peasy. Okay? You have the skills to do this. It's just like keeping the concepts straight that is the difficult part. But if you can write it out like this, it's a cinch. Okay? On the chi-squared, well, you draw the chi-squared on your critical value side, and you'd pick the two correct values after you do the little bracket, you know, 0.99, 0.01, 0.0, or 0.98, 0.01, 0.01, right? You just pick those two values. And instead of plus or minus, you actually are just adding both of them. You're actually not adding either of them because it's actually just all multiplication in that one. N minus 1 s squared over sigma squared. But you basically just do n minus 1 s squared times those two values. That'll give you the bounds, which is pretty cool. Let's just come back to this list really quick. We have covered, basically, yeah, talked about this kind of, right? If the what is the probability of getting a z-stat of 44? Later, Brenna. Is it less than or greater than the probability of getting a z-score of 2.32? It's way less. It's functionally 0. If you can keep that extreme example in your heads, this third line right here, this reject h naught, means that the probability of the test statistic is lower than the alpha. Just remember 44.7. It's so astronomically unlikely to see that the probability of seeing it, its p-value, is almost 0 if the null hypothesis is true, right? That's when we would reject the null hypothesis, because it is so astronomically unlikely that it is true, based on what we've seen. Okay, confidence intervals, I trust you'll be able to do that. You have the sheet of estimators, and that's actually going to be your biggest asset, is that sheet of tables and that sheet of estimators. So if there's like a proportion or a standard deviation confidence interval, I believe you have the skills to do that, quite frankly. Hypothesis testing, we've done that. All of them are the same. They're all on the sheet. One of them you have to flip around, but that's on the table. So just keep that in mind. Okay. We are not going to talk about adjusting estimators for bias anymore today, except for, let me tell you, that if you want to adjust the bias, I will point out to you really quick that the formula for sigma xy, later Natalie, that you've done is expected value of xy minus e of x, e of y. Please notice that x and y, oh wow! Why is this so far back? That's weird. Sigma hat xy, the formula that you guys have learned, is just a function of expected values of x and y, which is to say they're functions of estimators of the mean of x and y. So like x bar and y bar and like xy bar. If I wanted to adjust this telescope, if it were potentially to be biased, I would not be able to include something like an x or a y, or like something like a sigma. I can't put that into the equation, because sigma in itself is built into this part right here in the underlying math, that e of xy minus e x e y. It's just in there. Like, that's where we get sigma from, like, theoretically. I can't add that into my bias corrections. The only thing I can use to correct bias are things I know and can change. So like sample size n. And you guys know that sigma hat xy is equal to like n minus 1 over n, or actually in this case, when we corrected the bias of sigma hat xy, we did n minus 1 over n, and that turned it into sxy. Kind of annoying, TBA. Yeah, it's facts. Shaking in the boots. Amazing. Later, you guys. So just keep in mind, if you are going to adjust for bias, only do it with things that you're not trying to look at. Do not try to build your telescope, the estimator, or the fixed estimator out of a planet, the thing you're trying to look for. After that, that pretty much covers it. I didn't talk about passing E and V operators through. Hopefully at this point you know how to do that. If you don't, you can actually go watch, I think midterm 1 and midterm 2 reviews both talk about it. So I don't know if you picked up on it, but it's going to be a very important skill for you guys as this comes through. That's pretty much everything. You should be pretty well prepared for this test. If something has a bigger bias, it's more biased. If something has a bigger variance, it's less efficient. That's pretty much everything. I don't know which of these topics are going to show up on the test. It's less efficient if it varies more. So if the variance is higher, it's less efficient. If it varies less, it's less of a waste of your time, because you'll be seeing the thing you want to see more often because it doesn't move around as much. So that telescope is more efficient. But that'll basically cover everything. It's 11 a.m. Thanks for staying over. Hopefully you will find this useful. Hopefully I pondered the correct topics to share with you, whether it was laggy or not. So the question then, you guys are good to go if you want. Sam, my question for you is, like, do you also see the lag from what I'm saying to the iPad, or is it that you're getting it behind the rest of us? Because it's like the question is my camera desync from my iPad?
I think the camera and the iPad see. So the videos
Okay.
live here.
I think so, but I want to make sure that it's only that, right? Because like, it would only make sense if that were the case. But I want to make sure. So I'm asking Sam, but maybe he's already left because he left that thank you comment. That would actually be really unfortunate if he had done that. But I have 2 watching now, so there's someone else there. It could be Braden, it could be Sam. We're just going to wait. I mean, absolutely. Yeah, he's definitely gone. Those are some comments, huh? It's just... Wow. Very fine, yeah. Okay, Sam, that doesn't answer the question. So, like, the camera and the iPad are fine. Oh, you know what it is? There's so much of a delay, he didn't know I asked the question yet. Holy moly. Who names their kid Mount? Yeah, I'm very gone. Oh my gosh. All right, I'll stop the stream. That's fine. Hopefully I'll be able to figure that out. I mean, maybe next time I just do it in 114 Wyvern, Westview, Wyvern. I always, when I read WVB, I think like Wyvern building, like a dragon or something. It's like, I don't get it, man. The Wyvern. Are you guys heading to the Wyvern build? It's because in my head I want to say like WVB, because like you say like or like the JSB, right? But W has so many syllables that I'm thinking like WB or like, I don't know, something like that. Anyway, thanks for coming.
Thank you.
That'll